Welcome to the next session. Next up is Professor Hlér Kristjánsson on universal algorithm for transforming Hamiltonian eigenvalues.
Thank you very much for the introduction. Today I'm going to talk about a work that we started while I was a postdoc in a group of Murao in the University of Tokyo, and then continued after I moved to Canada, first to Waterloo and Montreal. It's joint work with Tatsuki Odake, who is a master's student in the group and did a lot of most of the technical work in this paper, and as well as Philip Taranto and Murao. So let's start with the introduction. So as we've seen many times this week, simulating physical systems is a key challenge in various areas of science. And quantum computers are expected to be able to help with the simulation of systems in an efficient way, specifically simulating the dynamics of a Hamiltonian on a quantum computer. There have been various works on this topic, as we've seen in this conference, and today I'm specifically going to introduce a paradigm called higher order transformations of Hamiltonian dynamics, which concerns itself with transforming black box Hamiltonian dynamics in a functional way. And specifically, I'm going to present an efficient algorithm transforming the eigenvalues of any Hamiltonian dynamics given as a black box by any sufficiently differentiable function. So let's start with a quick introduction to the simulation and transformations of physical systems. So in standard Hamiltonian simulation, we typically start with a classical description of Hamiltonian. So someone has written down on a piece of paper all the matrix elements of the Hamiltonian. Or potentially, in some certain settings, you have some oracle encoding additional information about the Hamiltonian, like a controlled version or a block encoding of the Hamiltonian. So what the task is you are given this known Hamiltonian, and the task is to construct the dynamics corresponding to the Hamiltonian for some time t. But in many scenarios, we might not actually know the dynamics of the Hamiltonian. In fact, that's one of the motivations for the quantum learning we saw this morning, learning of Hamiltonians this morning. So if we don't know the classical description of H, then we can't directly simulate it. But we might be able to consider a different task. So here, the task is that we are given some oracle access to the dynamics of a Hamiltonian, and we are interested in transforming that Hamiltonian dynamics by some function f. So you give me some oracle encoding e to the minus I h t for some unknown Hamiltonian h, and then someone else comes and gives me a function f on the space of Hamiltonians, and I give you back the dynamics of the transformed Hamiltonian e to the minus I f of ht. And this could be useful, for example, in complex or many-body systems, so we're not able to characterize the full Hamiltonian. It could be useful in analog or analog-digital hybrid computation, or in the Hamiltonian learning tasks we've heard about already. Now, the tools that we're going to use to construct this algorithm is based on higher order quantum computation. So I'll just give a very brief summary of this paradigm. So higher order quantum computation distinguishes itself from what I would call the sort of standard mode of quantum computation, which is in some sense a programming of quantum states. Typically, when we write algorithms, we have some input states. The quantum computer transforms the states through a bunch of channels and a whole circuit, and outputs another quantum state that you can then use for measurement. But taking inspiration from functional programming in the classical regime, we can also consider quantum functional programming, where the input to the computation is itself a quantum channel or a quantum circuit. And then a higher order quantum transformation takes that input circuit or channel and spits out another quantum channel. And there have been a lot of work in this direction recently, just about the last 5 or 10 years, with success in various areas, considering black box transformations of black box channels in a universal way. For example, universally taking a unitary and transforming it to its inverse, or its transpose conjugate, or even the control, which is in fact not really possible. But the other three have been various algorithms taking multiple copies of unitaries and performing these functions. So here we sort of extend this framework of quantum functional programming higher order computation to the space of Hamiltonians. So now we consider the transformations of Hamiltonian dynamics in such a functional black box way. So specifically now going to the algorithm, I will first summarize what the algorithm does. So we present a universal algorithm for transforming the eigenvalues of any Hamiltonian H just needs to be normalized with the standard requirement so that energies are not unbounded. So we're just normalizing this particular way. But in general, any Hamiltonian and any function f on the space of Hamiltonians that is sufficiently differentiable, in particular 3 times continuously differentiable. And the algorithm then takes multiple calls to the Hamiltonian dynamics e to the minus I h tau for various possible times tau, and spits out the black box containing e to the minus I f of ht for any chosen t that you want and any function f that you have chosen. The algorithm is deterministic and approximate with error epsilon, scaling essentially the main algorithm with 1 over epsilon, and then a presupposing step of epsilon to the 4. So a schematic of the algorithm is as follows. So what we do in the algorithm is that we alternate between applying some fixed gates in blue here, which may contain some correlated randomness. And we alternate that with applying basically short bursts of the evolution of the Hamiltonian that we're given as a black box, described here by this molecular picture. And the evolution times at each step, as well as the inherent randomness in these blue fixed gates, are sampled in a way that is analogous to the Q-drift Hamiltonian simulation algorithm for known Hamiltonians. And if you're not familiar with that, then you will see how it works later on in the technical part. And so basically, by alternating between fixed gates and the short Hamiltonian evolution bursts, we get the output being more or less deterministically and almost exactly equal to the simulated dynamics of the transformed Hamiltonian. So now to quickly describe how this algorithm is constructed. So we construct the algorithm in what we call a functional programming approach, where we concatenate several subroutines together which each act on black box dynamics, and we use them concatenated then to construct the algorithm in a similar way to the way you might construct an algorithm in functional programming in a classical algorithm design. So the first step, which we call actually step 0 here, is that so if we're not given access to both the positive and negative time, we just assume we have access to the forwards time evolution, e to the minus I h tau. Then, in fact, we had another algorithm 2 or 3 years ago, which allows you to, given any Hamiltonian evolution forwards, allows you to simulate the backwards time evolution. And so if you only have one of them, you can use that algorithm, get the second one. But for the rest of the talk, I'm going to assume that we have access to both the forward and backward evolution for simplicity. So then the next step is that once we're given either the positive or the negative, or in fact, we actually need both, but in each case, this subroutine called controlization, which is from a paper by Dong, Nakayama, Soeda, and Murao from 2019, takes as inputs a Hamiltonian evolution and returns a controlled version. And it does this by using a randomized algorithm. So the next step, number 2, is a subroutine that is developed newly in this work, which is Fourier series simulation. So here what we do is we assume as input some controlled version of the Hamiltonian. And essentially the algorithm simulates the Fourier series of the desired transform function f on this controlled Hamiltonian, both the positive and the negative time, and then returns the desired output Hamiltonian. So the total algorithm is the following. We concatenate steps 0, 1, and 2 to get something that goes from just the time evolution dynamics without any additional information, no control, no nothing, to the transformed Hamiltonian dynamics, which is itself also given as a black box. However, we find that actually, interestingly, this algorithm is not optimal in its time complexity. So what we can do, in addition, is actually maybe one of the most interesting things here, is a compilation step, sort of a higher order version of compilation in algorithms, where we now compile the correlated randomness, which occurs in all these different times, all these different subroutines, right? So each subroutine happens to be a randomized algorithm. And what we do is that instead of having each concatenated layer with some correlated randomness happening within that layer, we now correlate the different layers of randomness globally to make a more efficient version of the randomness. And we'll see this in some technical detail later. Okay, so let's move now to a more detailed view of the algorithm. So the first subroutine we'll consider here is the controlization. So the other one I mentioned, which takes positive to negative time, is the subject of another paper. And if you're interested, you can look up the reference after the talk. And so here, what we do is simulate control dynamics by basically we randomly sample some n-qubit Paulis. And we do that sort of sample the same one, and we run it twice. And in the middle, we sandwich those n-qubit control Paulis around the input Hamiltonian dynamics, run for a short time t over n. We do the whole thing n times, and the output you can show is equal to the controlled version of the Hamiltonian h0, which is the traceless part of h. And this runs with the time complexity t squared n over epsilon. The second part is now a bit more complicated. So we now start with a function f. Function f, okay, so there's a slight technical thing here. So instead of the function f, we actually deal with another function called f tilde, which is basically a transformed version of f to make it a little bit nicer to deal with, a bit more continuous. And then we just calculate classically the Fourier coefficients c tilde k of this function f. And we do it up to some cutoff number k, right? Because Fourier series of infinite numbers of terms, so we can't do all of them. So we do it up to some cutoff number k, such that this Fourier series up to k still simulates the right function with some error epsilon over 4t, which is 4t chosen for technical reasons. And now what we do is we sample this index small k, which is basically the index of which Fourier coefficient. So we sample the Fourier coefficients, or the index corresponding to Fourier coefficients k, with a probability proportional to the strength of those Fourier coefficients, so the absolute value of the coefficients. Now this is an analogy to the way that the Q-drift Hamiltonian simulation algorithm works, where you sample kind of, so the coefficients with a large amplitude overall are sampled more often than the Fourier coefficients that are less represented inside the function. And now we assume we have input the control dynamics, both positive and negative, and we just plug that as a sandwich, and around it, we now apply on one single control qubit this artificial Hamiltonian of the form cos phi k x minus sine phi k y, where phi k is now the phase of the Fourier coefficients. And then somehow magically, if you do the right calculation, we find that we get precisely what we want, e to the minus I f of h0t as the output of this randomized algorithm. So that's very nice. And now the next step is to do the concatenation. So this is actually just what we've seen before, and instead of calling the controlled version of the Hamiltonian, we call this sub 1k dagger, and where those sub 1k is basically the subroutine that creates the controlled evolution from the standard black box evolution. Okay, but yeah, as I said earlier, the time complexity now isn't as nice as it used to be. So now we have t to the 4n of epsilon cubed. And we would ideally like to go back to the t squared over epsilon type of scaling that we had for both of the previous subroutines individually. So how can we do that? Well, we notice something interesting. So you see here, like, this doesn't work. So here there is a sigma w, which is basically the index with which we pick these random Pauli. And then here's a u vector, which is the index of the other random Pauli we pick. In each within each step of the outer layer of the Fourier series simulation. So here, within each Fourier series simulation step, we pick twice the Paulis that we want to use to simulate the controlization. But actually, this, remember, is the positive time control Hamiltonian in the end of the day, and this is the negative time control Hamiltonian. So ideally, like, those two things should actually be conjugates of one another. So what we can do is correlate the U's and the W's and just to make a single index V. And that single index V now will be such that, around this artificial Hamiltonian in the middle, we now have the sandwich of the V1, both straight before and after, and then the V2, V3, and V4, all the way up to V10 k squared. And 10 k squared is also picked for some technical reasons that turns out it will work in the end. So basically, we correlate the multiple levels of randomness into a single random variable. And then we get this intermediate circuit, which we also showed on the previous slide. But unfortunately, some additional errors will be introduced here. So in order to mitigate those errors, we need to do something more. So the errors are actually just in the form of some z rotation, as well as some arbitrary real number ak in each kth step. Okay, and so what we can do is we can now run the circuit again many times, or run the sort of kth iteration of the circuit many times, and use robust phase estimation to obtain an estimate for those error parameters ak and the theta k. And then we use those estimates to slightly modify the probability distributions and the final iteration number, so which we call p accent k and n accent fk. And we plug those into the intermediate circuit now, and we obtain the final algorithm 4, which is just the same as the previous compiled version, but with modified probability distribution, modified iteration number, and of course a correction for the Pauli z rotation. Okay, and so now finally we will discuss a little bit and compare the two types of algorithms we discussed with the literature. So very briefly, so we see that a compiled algorithm, by doing this compilation step of correlating the randomness, we get back a nice scaling of the main process of t squared n over epsilon. There's still a pre-processing step that needs to be done once before any time the algorithm is applied, but then you can apply the same algorithm many times just with the main process. So in the asymptotic case, we care about the main process scaling. So we improved it from the uncompiled version. And interestingly, you can also do the same type of task with the QSVT-based algorithm. But of course, QSVT, as we've heard, cannot take as input just uncontrolled dynamics on its own. So a QSVT needs some block encoding. But again, our controlization subroutine can come to the rescue, and we can use controlization to get essentially a slightly modified version of controlization to get block encoding, and then apply standard QSVT Hamiltonian simulation methods on the controlled version of the Hamiltonian dynamics. And that gives us some other algorithms, some scaling. And the hierarchy is the following, that in general, the uncompiled version was the worst, so the direct concatenation was the worst performing. QSVT-based algorithm performs better in the asymptotic limit in terms of epsilon. And our compiled version, actually, the compilation step allows us to improve the performance beyond even that of the QSVT-based algorithm. So the compiled version of the algorithm, higher order algorithm, beats the QSVT version of the algorithm. So it's really nice that this compilation step is really seems to be really powerful as a model for this type of higher order quantum computation. Okay, so to summarize, in this talk we discussed the concept of higher order quantum algorithms, where given black box access to some Hamiltonian dynamics, we can simulate the functional transformation of this dynamics, or some function we like. And in particular, in this talk, I talked about the function f being some sufficiently continuous and differentiable function that acts on the eigenvalues of the Hamiltonian. And we presented a universal algorithm to perform this simulation. And we believe that this type of result, transforming unknown black box Hamiltonians to unknown black box Hamiltonians, could be of use in various areas, such as the simulation, learning and design of quantum systems. And really, like today, watching the talks on quantum Hamiltonian learning, it inspired me that maybe we could use this in that kind of area as well, or in some particular types of quantum simulation tasks. So yeah, if you like this work, please come and talk to me after. I'll be very keen if anybody has any ideas of applications or possibilities for future work or collaboration. So thank you very much for your attention.
Questions?
Thank you for the talk. I have two questions. One is, how this related to earlier works such as QETU and the GQSP for the same task, which stands for quantum eigenvalue transformations of unitary matrices and generalized quantum signal processing, respectively. And the second is, if I understand correctly, isn't the control-free implementation complementary technique to the task being performed here, rather than being merged into a whole thing?
Yeah, so maybe similar answer to both questions. So let's see if we can go back. So where is so yeah, I think so we did this comparison with the QSVT-based algorithm, and it's basically like two different algorithms that can do the same task, given a controlled version of the Hamiltonian. So I don't, that would be a very interesting question, but we have not calculated that one can be written in terms of the other. But once you have but the point is that if, in real physical experiments, you might not have access to the controlled version, so you might only have access to the real-time dynamics. And the point here is that with QSVT, you have to first somehow get the control dynamics, and even if you use this controlization subroutine, and then you apply the QSVT, those two algorithms are quite different in their structure. One is a randomized algorithm, one is a QSVT-based algorithm. And so what is nice here is that by using the Fourier series subroutine, which is also a randomized algorithm, the two steps can be concatenated together in a particular way.
Please allow me to be more explicit. One is QETU literally does this, and two is in the same paper, it talks about control-free implementation. And indeed, these are two complementary techniques rather than a whole technique.
I see. Yeah, I'm not so familiar with this, so maybe we can talk later.
Yeah.
Thank you for the talk. I just have a short question. The function, do you need like a white box version of it to get the Fourier series for it, or are you able also to black box the function?
So the function is just a classical function. So you would, you would write down the classical description of the function.
Yeah, the first question, I guess I forgot my first question, but let me go with the second. So I'm a little surprised the properties of F doesn't appear in the expressions. Are those in the constants?
Yes, exactly. Sorry. Yes, exactly.
By the way, I also remembered my first question.
So yeah, you see here there are some scaling. So here I only talk about time complexity. There are also numbers for total evolution time and so on. But just for simplicity, I didn't include them in this talk. But these constants here, like C3F, is some constant that depends on the function F precisely, and same with the QSVT-based algorithm. The K depends on F and so on.
Yeah, in particular, have you thought about another way to do what you did? It's a very naive way, but you can use e to the minus IHTs to do a phase estimation, and then register the energy to an ancilla, implement FH there, and back react this. Did you compare it to do it in that way? And can you exactly see this is better? Or
it's a good question. Yeah, we haven't thought about that, so I think you'd have to do the calculation.
Yeah, my first question very quickly. I understand the order, but what did you do to prove the lower bounds? Because I see theta's there.
So, sorry, which algorithm? The compiled algorithm.
Well, I believe you give a circuit that calls, time evolutions. That's, I can see this gives an upper bound.
Yeah.
But I'm wondering what did you do to prove the lower bounds as well?
Yeah, it's quite complicated. So
Right.
yeah, there are some techniques, but I don't think I can
I'll
explain right
check
now.
the paper.
Okay, I think that's all the time we have. Please, let's thank the speaker again.
Yeah.